what are these linear functions? We see on the screen here the definition. So we have here the function f between the vector space V and the vector space W. So the vector space V is the domain of our function, and W is the codomain. Well, I did not specify what V and W are, but for the moment let's assume it is generic. It's some vector space that we'll soon see examples. But right now it's just a vector space, meaning if you have two elements of V, when you combine those, well, you get another element of V. Similarly for W, and even the combination of W gives an element of W. So the first row here just says that we have a function named f, which assigns elements of V with elements of W. Well, on the second row, what do we find? Well, we have here V, a generic element of the vector space, the domain, which is assigned to f of V, a generic element of the codomain, and fv is paired V. So this is the input, this is the output. So far, what we have just described is just symbols saying that we have a connection, and we gave a name to that connection, f. So this is what we call the function. It states what are the sets, the input set and output set, and also states the name of the connection, and states what symbols v and f of v do we use for this assignment. So far, that's what we have. Now, so the word function checks so far. This is what we have here. But what about the word linear? We are talking about linear functions. And when we speak about linear functions, well, we want a very specific kind of connection between the elements of the domain and the codomain. And specifically, we want a connection in such a way that these two rules, A and B here, are verified. What do these rules say? Well, rule number A says that if you have V1 and V2, meaning two elements of the domain, so we are combining them. So you are combining elements of V, so you get another element of V, and that another element of V is named V1 plus V2, and the image of that element is not just is very special. It's a very special image, because it's special because it has to be specifically something like that. So FV1 plus FV2. Notice that, by the way, that this is an element of W, this is another element of W, and therefore a summation is another element of W. So you can see, on the left hand side we have an element of W, so this thing, the entire thing, the image of V1 plus V2, and on the right hand side another element of W. So it has to be specific, this element of W. Can you see? When you compute the image. Soon we'll see examples, specific examples of this, but so far, well, a function to be linear has to have this property. Additionally, it also needs to have the property B. The connection must be in such a way that this connection is true. And this connection says, well, if you have V, small v, an element of the domain, and you multiply it by a constant c, so you just rescale it. If it's one vector in one direction, you have, and c is 2, is twice of that. So it's c times v is another element of the domain. If you compute its image here, well, the output image must be specifically f of v times that c here. Can you see? This is a constraint, because when I write this, I have a function. There are many functions that we can construct between v and w. There are many. But I'm only interested on those where this thing is verified for any v1 and v2 and v, and also any number c. Whatever you put in here, this is always checks for the connections that this thing specifies. So this box and this box, well, is what we call a linear function. Linear functions. So this is generic. This is just a definition of the idea. So we are stating what we want. Downstairs, I give you an example. And what we find here is again the vector space V, the domain this time is R squared. So what is R squared? Let's remember what is R squared. R squared is a set. Is a set. It's a set whose elements are x, y. Right? It's x, y. It's order pairs. Where x, y are real numbers, right? Geometrically, R squared constitutes the entire plane. Each point on that plane corresponds to an order pair whose first entry, x, tells you how much you go along the horizontal direction, and the second entry, y, tells you how much you go on the vertical direction. So this is a vector space, corresponds to a plane. But on top of that, because this is just a set, we want a vector space. So additionally, besides R squared, you have also the operation of summation of order pairs and the multiplication of order pairs by constants, by numbers. Let's see one at a time. This is review. So far it's just review. Well, how do you sum, for example, 1, 3 plus 2, 1? Well, you sum entry-wise, right? Remember, you sum entry-wise. So we have the first entry plus the first entry means 3, and the second entry plus the second entry is 4. This is how you sum. Multiply by a constant. Well, let's put 10 times 1, 3. You get 10, 30. You just multiply entry-wise. So R squared plus these two properties, so you can sum and multiply by constants. Well, I'm not going to prove it, but I think you can see that whatever combination of order pairs in R squared always gives me another element of R squared. And so R squared is a vector space. It's more than a set. It's a vector space. So you have here the domain, a vector space, and here another element, another set, the codomain, another vector space, R squared. So it's the same thing. The elements that live here are order pairs, just like you see here. The elements that live on the codomain have the form given by this. Another order pair. But, as I wrote it, this order pair tells you how to compute it from the information xy, from the input. Well, if I have xy, I have 2x minus y, is an easy calculation if xy is given, and x plus y for the second entry. Also easy to compute, given the input. So this is how the pairing is done. You specify whatever input that you want from the domain, and we have a corresponding output. Additionally, I can give a nickname for this corresponding point on the domain. Let's call it fxy. This is a nickname, abbreviation for the corresponding element, the output element. So this is a function. It is a function because it assigns elements between two sets. It explains how to do the assignment, but is it a linear function? To check whether or not it is linear is a matter of checking whether a connection established like this obeys rule A and rule B. So let's check whether it is true or not. Let's check one at a time. For rule number A. Rule A, well, you just substitute. You substitute the information that you find here, there. and see whether the rule is satisfied. So for example, we have here f v1 plus v2. Well, v1 is some element of v, v2 is another element of v. It could be the same, but let's assume it's different. So what we have is, for example, let me write it, f of x1 y1 plus x2 y2. So this is the left hand side here. I specify v1 and v2. Is it true or not? This is the same thing of f x1 y1 plus f x2 y2. Whatever x1 y1 x2 y2 are, does not matter. But it is true. It is the equality holds. So let's put here. Is it true? Well, I already specified what is v1 and v2. I specified because, unlike this case, in this time I know specifically what the vector spaces are, and the vector spaces contain ordered pairs. So v1 and v2 now turn into ordered pairs. Here are two of them. So we already substituted on A that information, but you still have f here. We need to specify what we know about f. And the f, xy, it is the nickname, the abbreviation for this. So let's do it. Let's substitute this piece of information there. But before going to that, let me just write it like this: x1 plus x2, right? y1 plus y2. Can you see the idea? Now I can use this. Let's use this, because it is the order pair, which is a very big order pair, by the way. The first entry is 2x, so 2 times the first entry, but the first entry this time is x1 plus x2, so it's 2 x1 plus x2 minus y. But what is y? This is the second entry. But what is the second entry? Is y1 plus y2. y1 plus y2. Can you see how we do this? We just substitute what is generic here into something specific. Now, the second entry of of our linear function, well, it's x plus y. The first plus the second. But what is the first? Well, it's x1 plus x2 plus y1 plus y2. So let's write it. x1 plus x2 plus y1 plus y2. So far, so good. That's it. So, but still, we are just rearranging. We are just rearranging this thing so that we can check whether this side is equal to that side. So let's keep rearranging. Let's keep rearranging and see. Let's see it, because here it's separate, x1s and y1s, x2, y2. So let's try to split this thing as well. So let's try to do it. So we have 2 x1 minus y1, fine, plus 2x2 minus y2. Choose just rearrange. It's the same thing. x1 plus y1 plus x2 plus y2. But now, let's see what we can do. Well, let me just underline this thing. It's this part, right? And that part. You can split the thing. So it's 2x1 minus y1, comma, x1 plus y1, right? Plus the blue part. So it's 2x2 minus y2, x2 plus y2. Can you see the idea? But now, looking closely at these calculations, what we have here is f x1 y1, and here f x2 y2. Can you see? It's exactly the right hand side here. We just arrived there. So in fact it's confirmed. This equality A holds for this specific linear function that you find here. It just holds. But this is still not enough to call it linear. we need to check the second property. We need to check B here. So let's check the property B. Let's check B. B says what? Says, is it true or is it false that C times C, whatever number it is, times x, y, is it true or is it false, which is equal to C times f, x, y? Well, again, we just substitute what we know. What we know about f. And what we know about f, well, let's do it carefully. Cx, cy, fine, you just do this derivative, this times that. After all, V is a vector space, and we are allowed to do that. Now we have f of cx, comma, cy. What is that? Well, you just use the information above here. You just use this. This is what we know. This is how the connection is established. So let's use it. Let's use it because it's what's being called here. So it's 2cx minus cy, comma, cx plus cy. Fine. Now let's try. You see, because you already know the destination. We know the destination. If the destination suggests to us that we can factor C from x and y, well, let's try to do that. Let's try to do that. And I think you can see it. You can factor it, can't you? Can you see C? C is everywhere, so it's have a C. C 2x minus y, x plus y. It's done. What we find here is f x, y. So the property B holds for our linear function, for our function that we have. Therefore, we can say confidently that this connection, which is described here, is indeed a linear function. That's it. You need to verify these two properties. So what you see here is not just any connection. It is specifically a connection where A and B hold.